and welcome back to Engineering Illustrated. Today we have a 3D vector that we want to resolve into its Cartesian components, fx, fy, and fz, which are the amount that the vector travels along each axis. First off, we can see that we have a 3, 4, 5 triangle relating f to the z-axis and a 30-degree angle relating it to the y-axis. When we're working with 3D vectors like this, we actually need to perform two separate operations to find all three components. First, we need to break f into fz and fxy, like that. Fz is along the z-axis, and fxy is on the xy plane. It's not along either axis. Once we've done that, we need to break fxy into fx and fy, which are its components. Z doesn't have an effect on this part. Once we've done that, we have our Cartesian components. When I'm solving problems like this, I always like to draw simplified pictures to not have extra information floating around. So let's look normal to that purple triangle, which means look directly at it. Now we're dealing with a 2D problem. The left side is a z-axis, and the bottom represents the xy plane. And we want to find the components of f in those two directions. First, we're going to use similar triangles to determine the side lengths of this triangle. For an explanation of why this works, check out the video in the top right corner. So Fz is going to be equal to, by similar triangles, 500, which is the magnitude of our force, times 4 over 5, which is going to come out to be 400 newtons. And Fxy, similarly, will be 500 times 3 over 5, which comes out to 300 newtons. Now that we know Fz, we can take care of Fxy and see if we can't break it down into its components. Let's look directly down at the xy plane for that. Whenever I'm redrawing diagrams like this, it's always worth checking the original picture to make sure it gets drawn correctly. In our case, our vector is 30 degrees from the y-axis. Once again, our goal is to break fxy into its components, fx and fy. This time we can't use similar triangles, so we'll use trig. Just a quick review of SOHCAHTOA. SOHCAHTOA tells us that cosine of 30 will give us fy and sine of 30 will give us fx. So that means fy, which is right here, this is fx, fy equals 300 times the cosine of 30. And that comes out to be 259.8 newtons. And fx equals 300 times sine of 30, which comes out to be 150. Now we have all three Cartesian components of our original vector f. Going back to our original picture and labeling the components, we can see how the three components add up to give us the vector f. F in Cartesian form is 150 newtons, 259.8 newtons, and 400 newtons. Now at this point, it's always a good idea to check your work to make sure nothing went wrong along the way. And a quick way to do this is to calculate the magnitude of the combined component that we just calculated. This is done by a square root sum of the squares, or I like to think of it as a big Pythagorean theorem. And if we run that calculation, we see that it does indeed come out to 500 newtons. I put the squiggly equals there because 259.8 is a rounded value, so the calculator actually spit out 499.996, but I think that's close enough to prove that it worked. Now once again, thank you for joining me in this video. I hope that it was helpful, and I hope that it was able to show you that these 3D vectors aren't quite as bad as they look. It just takes breaking them down into two separate pieces and treating them like 2D vectors. I hope this was helpful. Thanks for watching. My goal is to create concise and relatively easy to understand content for undergraduate engineering classes. Let me know in the comments how I can improve, and what you'd like to see in upcoming videos. Thanks!